In our previous meeting, we were talking about drawing Lewis structures. We looked at the series of rules for the process of drawing Lewis structures. And the purpose of drawing the Lewis structures was to allow us then to predict the geometric shape of either the molecule or the ion species that we might be working with. The last one that we looked at was the nitrite ion, as it is called, NO2, and we did that right at the end of the period and kind of hurriedly. So let me go ahead and at least put this back together with the way it looked and then talk a little bit more about the geometric shape. So we ended up, when we did the Lewis structure here, with a species that had to have now a double bond in it, and the oxygens then would have ended up each with these extra pairs, and the nitrogen would have one pair on it. And that was the Lewis structure, except that I should indicate here that it is a ion, it's a minus ion then that we're dealing with. Now, as far as the geometry was concerned, and somebody asked right after class how I came up with the geometry of a bent molecule, they said, shouldn't it have been triangular because we had 3 electron pairs around the central part? Well, let's look at this again. We do have 3 effective electron pairs around the central group. 1, 2, and the double bond counts as only 1 as far as geometry. So we do have 3. So if we were going to draw this out, we would draw nitrogen and then a pair of electrons, but those are the non-bonding electrons. We've mentioned those before, non-bonding electrons. Then we would have this double bond oxygen, and we would have a single bond oxygen. So the 3 groups, 1, 2, 3, are in fact in a triangular shape. However, we cannot see the non-bonding electrons, and if we take that part of it away, of course, we're only left then with a molecule that just looks, or an ion in this case, that looks bent. Can probably demonstrate that using this model here as well. We have 4 electron pairs essentially here around the nitrogen. It has its octet, so we have put them in forms of a tetrahedral. Now, to one of these pairs of electrons, we're going to put an oxygen atom. So we'll put an oxygen atom on there. To 2 pairs, now, we're going to put 1 oxygen on 2 pairs. So I will take springs here so that I can have some flexibility, and I will attempt to put it together. So now we have the oxygen with the double bond to the nitrogen, and the oxygen with the single bond to the nitrogen, and then the pair of non-bonding electrons. Well, if I can't see that pair of non-bonding electrons now, you see then the shape of the ion is, as we would indicate, an angular or a bent shape. All right? So that's the way we came up with the geometry for that particular species. Let's go on and take a look at one more here. And we'll do the Lewis structure first and then predict the geometric shape. The molecule CH2O. Now, again, the steps of Lewis structure, we add up all the valence electrons. So we have 4 for the carbon, 2 for the 2 hydrogens, 6 for the oxygen, and we end up then with 12 or 6 electron pairs that we have to work with. Now, the first thing we do then is we attach each species to the central atom with a single bond. The central atom is the carbon here. So we're going to have carbon, an oxygen, a hydrogen, and a hydrogen. Now we have used up 3 electron pairs to make our single bonds. So we have 3 electron pairs left. The question is, how many electron pairs would we need now to give everything a noble gas-like structure? Well, we would need 3 more pairs on this oxygen because it only has 1. That would give it an octet. And we need 1 more pair on this carbon. That would give it an octet. So we need a total of 4, but we have only 3. And of course the rule is that for each electron pair that we are short, if possible, we will put in a multiple bond. By that I mean that there are only those 6 or 7 elements that can form multiple bonds. Once again, carbon, nitrogen, oxygen, and the 3 elements under those, silicon, phosphorus, sulfur, and under sulfur, selenium to a small extent, are the 6 or 7 elements that can form multiple bonds. Well, we see both carbon and oxygen are one of those 6, so in fact we can form a multiple bond. We needed 4, we had only 3, we're 1 short, we need 1 multiple bond. Well, the only place we can put it would be here, and then of course that carbon now has an octet, so we would give this oxygen 2 more pair, adding up our total number of electron pairs now, 1, 2, 3, 4, 5, 6. We started with 6, and so we have the correct number of electrons indicated. Now, what about the geometric shape for this species? Well, again, then we count the number of electron pairs around the central atom. Multiple bonds count the same as single, so we have 1, 2, 3. So that tells us that this here should in fact be triangular in geometry. It should be triangular, and it should be then planar as well. So in other words, we would have carbon, double bond oxygen, 120 degrees from that would be a hydrogen, and 120 degrees would be the other hydrogen. We can go back to our same species that we started with a moment ago. The only difference is here now we're going to have a couple of hydrogens that we put on. So we start with carbon, 4 electron pairs around it, as we've shown. We have the oxygen, which is going to form the double bond with the carbon. So now we've got the oxygen double bonded to the carbon, and now we're going to put on 2 hydrogens. And so in fact we see then that the molecule is triangular. As a matter of fact, it's equilateral triangular, and it is planar. In other words, everything is in a 2-dimensional rather than a 3-dimensional structure. So we can show the geometric shape then of molecule involving the multiple bonds or single bonds by using this method. All right, any questions on any of those? Now we have looked at, and we'll just look at one more here quickly, we have looked at those Lewis structures in which everything didn't satisfy its octet. BCl3, for instance, we had boron, 3 electrons, and for chlorine 3 times 7, 21. So we had 24 or 12 electron pair. And we started then, we hooked each chlorine to the boron. So we used up 3 electron pair. And that left us with 9 electron pair to work with. Now, looking at the structure there, we can see that we would need 3 more pairs on this chlorine, 3 on this one, 3 on this one, and 1 more on the boron to give everything an octet. That would be 3 plus 3 plus 3 plus 1 for 10. We have only 9, so we're 1 electron pair short, which would predict that we should have a multiple bond, but again, only if it's one of those 7 elements. Neither of these are one of those 7 elements, so therefore we cannot form a multiple bond. That means that something is not going to be able to satisfy its octet. The question is, which one of these species is the one that's not going to have its octet filled? Well, the rule is that the elements furthest to the left will be the ones that will be least likely to attract electrons. Remember electronegativity. Chlorine over here has a higher electronegativity than does boron. In other words, it has a greater attraction for electrons, and therefore we would give the 8 electrons to each of the chlorines. We'd satisfy its octet, and the boron, which has less attraction for electrons, would be left then electron deficient. So we would finish this structure then by giving each of the chlorines now those pairs of electrons, and we've now used up everything, and that is the correct Lewis structure. Geometrically, once again, we have 3 electron pairs around the boron then, and of course this molecule then would be triangular in shape. All right, that's one type of exception to the octet. But we also have another type of exception to the octet, and that is for a few elements, we find that they actually exceed the octet of electrons. This is not something we would necessarily predict, but it's something that we do find. In other words, in nature, there is a molecule with a chemical formula PCl5. Now, neither phosphorus nor chlorine can form multiple bonds. And so if I'm going to put these together, this PCl5 now, the only way that I can put that PCl5 together, excuse me, is to attach each of the chlorines now to the phosphorus. If we add up all the electrons here, phosphorus is in the 5th column, so we have 5, and then chlorine, or 5 times 7 would be 35, so we have 40 electrons, or 20 electron pair. We've used up 5, okay, and then we would need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 more, and of course that's what we have. And so everything there, all the chlorines have octets. They all have 4 pairs of electrons. But notice the phosphorus now has how many pairs of electrons around it? 5 for a total of 10. So its octet has been exceeded. And yes, this molecule exists, so this is the way we have to draw the structure then to represent it. What about the geometric shape? Well, we haven't really said anything about the geometric shape of these that exceed the octet. The shapes that we had in the table with the Lewis structures were only for those that were less than or equal to an octet of electrons. Well, it turns out then that the geometric shape for that particular species is like a pyramid, except that we have a double pyramid. So in other words, we have a pyramid stacked on top of a pyramid, upside down, the 2 bases together. This would be one pyramid, and this would be the other 3-sided pyramid. And so we specifically refer to this shape as bipyramidal structure, a double pyramid stacked base to base. All right? And we see that On the equator, I guess we could call it, on the equator the atoms are 120 degrees from each other. Of course, obviously these two are 180 degrees from each other, and these are 90 degrees from each other. It's impossible to put 5 things on and get them all equal distant from each other. And so this is the geometric shape that has been determined by X-ray diffraction for this type of structure. All right? So we have then a bipyramidal shape. We also have one other one, sulfur hexafluoride. Matter of fact, sulfur hexafluoride has been used for many years as an insulating material, as a non-electrolyte in transformers. In transformers where you have very high electrical charges, you don't want any kind of internal electricity flow or sparking to occur, and they use then a chemical in there that's a non-electrolyte to insulate it, a liquid. And the liquid that was used for many years was sulfur hexafluoride. Now, with our concern about fluorine and the ozone layer, then this compound has been removed as far as being an insulator. As transformers wore out, as transformers were replaced, they were then replaced with transformers that no longer contained this hexafluoral compound. But again, if we look at this, fluorine can only form single bonds. Now, sulfur can form multiple bonds, but that doesn't help us with fluorine only being able to solve or form single bonds. We have 6 from the sulfur. 6 times 7, that would be 42 from the fluorine. And so we have a total of 48 electrons, or 24 electron pair. Well, if we go ahead then and start with the sulfur, and we hook in now the 6 fluorines, like such. We have used up 6 electron pairs, which means we have 18 electron pairs left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so all of the fluorines have their octet, but the sulfur has exceeded the octet. It actually has now 12 electrons around that nucleus. Again, geometrically, we haven't said anything about that shape, but the shape of it looks like this. We see that we have a square shape here or a square shape there. No matter which way you turn this, you have a square shape. So it's kind of like a square pyramid stacked on top of a square pyramid. I guess we could call it that way. But actually, the way they name it is based on the number of faces. We have 1, 2, 3, 4 faces, and of course we'd have 1, 2, 3, 4 faces below, so we have a total of 8 faces on that structure. And of course the prefix for 8 is what? Prefix for 8? Oh, certainly somebody knows. Prefix for 8. Octa. So this is called octa. And of course the word that we use for face, octahedral. So that's an octahedral structure for that particular molecule. Whoops, and that was a weak fluorine sulfur bond that we saw there that broke. Okay. All right. So neither of these are we going to worry about in terms of that we will have to necessarily name that structure, but the fact is that that is the geometry that we would get. Now, in the bonding that we've talked about so far, we've talked about 2 atoms, each contributing 1 electron from one of its orbitals, one of its valence orbitals, to form a bond. But we can also have a type of covalent sharing process in which one of the species provides both electrons and the other provides none. And this is referred to as coordinate covalent bonding. And here's an example of a coordinate covalent bonding condition. Ammonia reacting with a hydrogen ion to form ammonium. Now, if we look at the structure of the ammonia here, it would look like this. It would be a pyramidal structure, and it has a pair of electrons. Hydrogen ion is merely an empty s orbital. I mean, hydrogen only has one electron, and if we have a hydrogen ion, it is nothing more than a proton with an empty s orbital. So we can see this hydrogen then could actually sit down on top of that pair of electrons, its empty s orbital, and form then a covalent bond, and we'll end up with the molecule now that looks like this. Still will have now a tetrahedral shape, except that it is an ion. Now, once it is formed, I would not be able to tell which one of those 4 bonds in there was the one that was a coordinate covalent bond. They're all still the same bond energy. But the pair of electrons used to form the bond initially came from only one species then, and that's called coordinate covalent bonding. Now, notice that the ammonia has accepted a proton. And what did we define something that accepted a proton? Chapter 5, you better know this because this could be on one of the exams. What did we define something that could accept a proton? Bronsted-Lowry definition. What? I heard somebody say. An acid. Nope. Got a 50-50 chance, so all right, we'll take the base then. Something that can accept a proton, remember by definition, an acid is a proton donor. Bronsted-Lowry definition. A base is a proton acceptor. So the ammonia here has accepted a proton to form this ammonium ion. Now, Lewis, who is the one, of course, that we're talking about, Lewis structures, Lewis then said, what is it that's really involved in acid-base reactions? It really isn't the proton, it's electrons. Electrons form bonds. Why don't we define acids and bases then in terms of bonds, in terms of electron pairs? And so Lewis then said, we can define a base then as anything that has an electron pair to donate. So a base is an electron pair donor. In other words, it has a pair of non-bonding electrons that it can donate or share to form a chemical bond. And obviously, if we call a base an electron pair donor, then an acid becomes an electron pair acceptor. So, Lewis then gave us a new definition for the acid and the base. And actually, Lewis's definition of an acid and a base now adds some things to acid categories that previously were not included in acids. Because before, anything that was an acid had to have essentially an ionizable hydrogen, a proton to give away. Now we're saying the only thing you have to do to be an acid is be able to accept a pair of electrons. And there are many compounds that fit into that category. If you go on to take a course in organic chemistry, for instance, you'll probably talk quite a bit about Lewis acids and Lewis bases. They're very weak acids, but they're involved in organic chemical reactions quite extensively. Now, one of the places that we're going to run into these Lewis bases, then, are in a group of organic compounds called heterocyclic amines. Now, we've already talked about the group amines in the chapter on acid-base. Recall that an amine has a general formula that looks like that. It has a nitrogen in it, and this nitrogen does have a pair of electrons. As a matter of fact, it's that pair of electrons on the nitrogen that makes the molecule a base. All right? Those are the organic bases. These are amines. They're called cyclic because obviously they're hooked together in a cycle. And they're called heterocyclic because in the ring structure they have an atom other than a carbon. Now, if all of these were carbons, and we talked about one of those, we talked about it the other day. As a matter of fact, we had this one here in which we had the 6 carbons. I don't have a lot of room to draw here. The 6 carbons with alternating double bonds. And remember, we called that benzene. Benzene was a cyclic hydrocarbon. It is referred to as a homocyclic because all of the atoms in the ring are the same type. They're all carbons. That's a homocyclic. Heterocyclic means at least one of the atoms in the ring in the cycle is not a carbon. That's what heterocyclic means. And we see each of these has at least one nitrogen in its structure. And each of these nitrogens has a pair of electrons, non-bonding electrons. This particular one has 2. Non-bonding electrons that can be used as a base, as an electron pair donor to something else. These will become very important to us in Chapter 14 as we begin to talk about nucleic acids. Nucleic acids all involve one of these heterocyclic amine structures as part of the overall molecular structure. So we'll come back and look at that. But again, it's this pair of electrons that allows it to be a base. As a matter of fact, everything that serves as a base, whether it be this or ammonia or even just the hydroxide ion, the reason the hydroxide ion serves as a base, that's the Lewis structure for the hydroxide ion. The reason the hydroxide ion is a base is it has a pair of electrons that it can donate to a hydrogen ion to make a water molecule, an acid-base reaction. All right? Now, one of the key functions of drawing Lewis structures is to be able to talk about molecular polarity. Now, polarity of molecules, not polarity of bonds. We've already talked about polarity of bonds. Polarity of bonds means that there's an electronegativity difference between the 2 atoms that are attached. That's all. If they have an electronegativity difference, they are a polar bond. But a polar molecule then involves not only polar bonds but also the geometry of the molecule. Now, to be a polar molecule, number 1, you must have polar bonds. You can't be a polar molecule if you don't have a polar bond. But number 2 is you must have the correct geometric shape. As a matter of fact, we sometimes say that molecular polarity is the vector sum of electronegativity differences, delta. The vector sum of the electronegativity differences. In other words, vectors indicate direction and magnitude of electronegativity difference. Let's take, for example, water here as our molecule, and we've done the Lewis structure now, and when we do the Lewis structure for the water, and of course we would have a couple of non-bonding pairs there, We do the Lewis structure, and then the geometry would tell us that this is a bent molecule. As a matter of fact, the bond angles in here are about 109 degrees. Now, when I talk about the vector sum, I'll start down here then. Now, I'll put this as the oxygen center. Now, I see that I have two vectors. Oxygen has an electronegativity, I'll put this down in here so we can see it a little bit better, 3.5. Hydrogen, 2.1. So there's an electronegativity difference between those two of 1.4. And oxygen is the one that is more strongly attracting, so we would draw the vector then in the molecule here as acting toward the oxygen. So the oxygen would be negative, the hydrogens would be positive. Now, let's talk about the total vector in the molecule, however. So, if I start right here, then, and I'm going to take the first vector, which was a difference of 1.4, and it was angled up, then at a direction up in this way, so we'll call each block about 0.2. So we'll go up about 7 blocks here. 1, 2, 3, 4, 5, 6, 7, something like that. That's my first vector. That was 1.4 units from the oxygen. We're saying that we've displaced the electron charge that much. Now I would start there, and the other vector we see now is going to be about 109 degrees, so not quite 90, but about 109, a little bit further, and it's also 1.4. And so we go up here now about 7 blocks again, and we should end up about right there. Now, when we add these two together graphically, then we end up with a net vector. This is the vector sum right there. So we're saying that we have a net vector acting in the molecule, then in this direction through the molecule of a certain magnitude. We don't care what it is. It looks like in this case it would probably be a magnitude of about 2.0 or something like that. But we have a definite vector, so this side of the molecule is definitely negative, and this side of the molecule is definitely positive. And so if I'll just draw the water over here, then I'm saying that my vector is like that. This is the negative side, this is the positive side, and so we definitely have a polar molecule. We have polar bonds, but the geometric shape also gives us then a vector that doesn't add to 0. If the vector adds to 0, it would mean that we would have a non-polar molecule. If the vector adds to any numeric value, we have a polar molecule. Now, what's the importance of polarity? Well, one of the things when we talked in Chapter 4 about dissolving is we said that likes dissolve likes. Why does water dissolve ethyl alcohol and carbon tetrachloride not? Because of the molecular polarity. In Chapter 10, we'll talk more extensively about liquids and solids and some of the physical properties, melting points, boiling points, density, and it all will tie back into this idea of molecular polarity, or at least that will be one of the major contributing forces that we'll have to take into consideration. Well, let's try another one here quickly. Just a moment ago, we drew the Lewis structure for BCl3, and we came up with this for its geometric shape. Now, electronegativities, boron has an electronegativity of 2.0, and chlorine has an electronegativity of 3.0. So yes, we do have polar bonds. We would have a vector going that way, and this way, and this way. And each of those would have an electronegativity difference of 1.0. Well, let's try to depict this now on the graph. So once again, we'll start right here. That's the center before we look at any of the vectors. And let's take then our first vector up here, and we will go up, and again we'll use 0.2 per block, so we're going to go up 5 blocks. 1, 2, 3, 4, 5. So we're going to take our first vector up to there. Then we'll take this vector, 1.0. It's going to start at this point, and it's going to go 5 blocks now to the right and down. So it's going to go like this, 5 blocks. And then we're going to take this vector, which is also 1.0, and it's going to go 120 degrees in this direction, 5 blocks. And where did we end up? We ended up where we started. What's the net vector when I add all those up? 0. I'm right back where I started. There is no charge displacement in that molecule. There is no positive and negative side. As a matter of fact, all of the chlorines are partially negative in that structure. There isn't a positive end and a negative end, or a positive side and a negative side. It's all surrounded by negative chlorines in that case. So, therefore, BCl3 is a non-polar molecule. All right, if you have any questions, raise your hands, or we'll just keep blasting forward. Carbon dioxide. If I do the Lewis structure for carbon dioxide, we will have this for the Lewis structure. And if we were to look at the carbon here now, with essentially 2 electron pairs around it, around the carbon, what would be the geometric shape of carbon dioxide? Linear. Absolutely right. Linear. All right? So that means that both oxygens are on opposite sides. Carbon, 2.5, oxygen, 3.5. So we have 2 vectors, one going that direction and one going that direction, and at 1.0 magnitude. Again, if we take our chart here and we start here, and then we'll take the first vector up there, 1.0, and we go over there, 5 squares, again using each square counting as 0.2, and then I take this vector and start where I was, and I go this direction, 1.0. Where am I? Right back where I was. There is 0 charge displacement in the molecule. Carbon dioxide is a non-polar linear molecule. So the Lewis structure gave us the ability to predict the geometric shape, and then knowing electronegativity differences, we can determine the actual polarity. Now, does carbon dioxide dissolve very extensively in water? No. Hardly at all. Matter of fact, it's very difficult to get carbon dioxide in water. That's why when you take the cap off a carbonated beverage, all the carbon dioxide comes rushing out. It doesn't want to stay dissolved. The only way we can get it in is to put it in under high pressure in the first place. Why wouldn't it be soluble in water? Well, what kind of molecules are water molecules? Just drew it a moment ago. Polar. What kind of a molecule is carbon dioxide? Nonpolar. Nonpolars do not dissolve in polar solvents, and so therefore we would expect CO2 does not have very much solubility. Question? Do I have a question? Okay. All right, this is formaldehyde. An organic compound. It's a type of compounds that we haven't talked about as far as functional groups, but this is formaldehyde. And we will talk about the aldehydes and ketones, 2 other organic groups, a little bit later. If we do the Lewis structure, again, we come up with this. We just did the Lewis structure for this one a little bit earlier in this lecture today. And we came up with then a geometric shape that this will be then triangular, because the double bond counts as 1 and then the other 2, so we have 3, so it's planar and it's triangular. Now, electronegativity wise, hydrogens are 2.1, carbon is 2.5, oxygen is 3.5. Those are our electronegativities that we're going to work with. So we have a vector acting in this direction with a magnitude of 0.4. We have a vector acting in that direction with a magnitude of 0.4. And then we have a vector acting in this direction with a magnitude of 1.0. Now, if we go down to our graph paper here, and we start here in the center, we take our first vector, which was the hydrogen-carbon vector, 0.4, and so we will use, well, let's see, this time I guess we could use, we'll use 0.2 again per block. So we'd go over about 2 blocks down here in this general direction for our first vector. Our second vector starts where our first one left off, and we're going to go about 2 blocks, which would be 0.4 units at 120 or 109 degrees, and we're back there. And then we're going to take our last vector, which is 1.0, starting here and going over then 5 blocks, and we're right there. If we add all these together to get our net vector, here's where we ended up, here's where we started. Our net vector would be that. So is this molecule polar? Quite definitely so. This end is the negative end, this end is the positive end. The point of the arrow is always the end where the electrons are moving to. And so if we were to go back up here and redraw this quickly, like such, we would say this side is partially positive and this side is partially negative, and formaldehyde is a polar molecule. And would I predict that formaldehyde should dissolve in water? Yes, because polar solvents like polar solutes. Nonpolar solvents like nonpolar solutes. We talked about that in chapter 4 a little bit. All right. Let's look at phosphorus, and let's look at PH3 first of all. And we'll also look at PCl3. Now, if we look at PH3, it's going to have this same geometric shape. It's pyramidal. There's that pair of non-bonding electrons, but as far as the geometry is concerned, then we'd have phosphorus with a hydrogen and a hydrogen and a hydrogen. Question is that polar or nonpolar? It gets to be a little bit difficult when you go to 3-dimensional molecules, because now you have things moving into and out of the 2 dimensions, and so it's a little bit more difficult to plot. But we can make some rough estimates and we'll see. But first of all, in the case of PH3, we look up hydrogen's 2.1, and if we look at the electronegativity table, which I forgot to bring along, I believe I'm correct on this, phosphorus is 2.1. Well, I really don't need to go any further in this case. The geometric shape of this would look like, if I go back here to the center, that all of my vectors are going to be either toward the phosphorus, away from the phosphorus. So they're going to be something like going down this way, then going down this way, and then coming out at us. So if the attached group was more electronegative than the phosphorus, we'd end up with a net vector like that. Or if the attached group was less electronegative, then the vectors would go towards it, and so we would end up then with something going like that, and then like that, and then like this, and we would end up with this as our net vector. So it should be a polar molecule if, in fact, there are electronegativity differences. But with phosphorus and hydrogen, we have a nonpolar bond, and so even though the geometry is such that it should be polar, it can't be polar if we don't have polar bonds. In contrast, here we would have 2.1 and 3.0, and so therefore we do have an electronegativity difference, and the geometry would then tell us that yes, in fact, we should have a polar molecule. Now, in general, for pyramidal or tetrahedral type structures, which are going to be three-dimensional, one can basically use it in a two-dimension to get a good estimate of the vectors. Not quite accurate, but pretty close. In other words, we could just say that we were looking at it like this, so that we're looking at a two-dimensional, and we're going to have about the same effect. This vector would offset this vector, and we would end up with a net vector here, so that yes, if the electronegativity was different, we would have then a polar molecule. So one can force them back into two dimensions to kind of look at molecular polarity. All right, any question on any part of that one? Okay. One other one would involve the tetrahedral geometry, like around the carbon center, and again, as we see there, we would have a three-dimensional molecule to work with, but we could again get a pretty good estimate by looking at it in terms of a square. Now, let's suppose that we were looking at methane, CH4. Methane, carbon is 2.5 and hydrogen's 2.1. So yes, there would be an electronegativity difference, and yes, there would be a polar bond. But if we went down here then, now looking, our vectors would look like this. Each one would be 0.4. So we would go over 2 blocks, down 2 blocks, over 2 blocks, and back up 2 blocks. And where are we? Nowhere. We're right back where we started, and so methane, CH4, would be a nonpolar molecule. CCl4, carbon tetrachloride, would be a nonpolar molecule. But what about CH2Cl2? What about it? If we look at it in terms of square planar condition, now we'll put, doesn't make any difference where we put these. We can put them that way. Yes, it does make a difference now. So if we draw it that way or versus drawing it this way, we would have two different effects. And so when we get to mixed around the tetrahedral, we really do need to picture it three-dimensionally to determine molecular polarity. Well, in our next lecture, we'll take a look at isomerization and its effect on geometric shape, and go on and begin a little bit of Chapter 8 on chemical nomenclature. In Chapter 7, at the end of the chapter, we've been talking about molecular shapes and molecular polarity. And we're going to take a look today at a couple of molecules and see how we can demonstrate this molecular polarity. The shape of water molecule is such, and the shape of ethyl alcohol molecule is such. And if we were to look at their vector sums, we would find that, in fact, they were both polar molecules. The molecule we have here is carbon tetrachloride, and it would be tetrahedral in geometric shape, and the vector sum would be 0. It would be a nonpolar molecule. And iodine, which is two iodine atoms connected together, would also be a nonpolar molecule. Now, if we took one of these two liquids that are polar and considered them to be like little plus and minus magnets, if we were to bring a charge to the side of a tube of the liquid, we would anticipate that the molecules would orient themselves in such a way that the opposite charge would be attracted to the external charge that we have brought along. And so we're going to use this principle to try to demonstrate then how we can show that something is polar or nonpolar in the liquid state. Then we'll continue by taking a look at this phenomena of polar and nonpolar molecules. Now, I have set up a demonstration here, and I have three liquids. The first burette contains water. We know that it's water because it's blue. We've got ethyl alcohol, or sometimes by the moonshiners called old red eye, so that's why it's colored there. It's ethyl alcohol with just a drop of food coloring. And the last small tube we have is carbon tetrachloride with a small amount of iodine in it to give it the purple color so that we could see it. All three liquids themselves are colorless. This is just merely that we can visualize them better. Now, we need a charged rod in order to check the polarity and nonpolarity. And so what I have here is a piece of cat fur and just a plastic ruler. And if we do a little friction, hopefully we can get a charge on this. And we can check with the pieces of paper, and we see that, yes, we do have a charged sphere. All right, we now again will charge up our rod here. We're going to turn on a stream of the water. We can see that it's flowing down straight. If I bring the charged sphere up, we should notice then a bending of the stream. I'll try to bring it in from the other side, and with luck, you can maybe see that I'm now putting it into the large beaker between the two burettes. This is not a physical contact. There's no liquid here. It is merely the fact that the water, which is polar, is attracted to the charged rod. Now we'll try the ethyl alcohol, so we'll turn a stream of the ethyl alcohol on. Again, we see that it's going straight into the beaker. If I bring the charge up, we see that the stream of ethyl alcohol is being curved. And if I bring it this side, I hopefully maybe can bring it into the large beaker. If I can get it going the right direction here. Well, we can't quite get it to go into the large beaker. Now we're going to test the carbon tetrachloride, and again we'll get a charge on here quickly. We see that it is charged. I'll need to switch sides here. I will turn on the stream of carbon tetrachloride, and as I bring up the charged rod, we notice that nothing is happening to the stream of carbon tetrachloride, indicating it is not attracted to the positive or to the negative charge. Now, one might ask, maybe it's because this thing has lost its charge. Let's just double check quickly. We see that is not the case, that the ethyl alcohol is bending profusely, so therefore it is charged. We can go back quickly then and re-show that the carbon tetrachloride is not affected, thus showing that it is a nonpolar molecule. Now we're going to take a look at the compatibility of liquids. If you recall in Chapter 4 on solutions, we talked about that like materials dissolved like materials. In other words, polar molecules like polar molecules, and nonpolar molecules like nonpolar molecules. We have the water and the ethyl alcohol, both which are polar, and if I pour them together, we notice that we get a color mixture, but it is a pure solution. It is not separating into individual layers. So both liquids are totally miscible in each other. So we see then again that polar like polar. If we were to take some of the carbon tetrachloride, which is nonpolar, and add some water, which I have done in this tube, we see that they separate into two separate layers. The polar water molecules do not like the nonpolar carbon tet. If we shake this up, let it stand here for just a second, we quickly see that the molecules literally squeeze each other out. The nonpolar go back to being in the nonpolar layer, and the polar water molecules have squeezed out the carbon tet and are making once again the colorless water layer. So again, we see a demonstration of the miscibility and immiscibility of different liquids depending upon if they're polar or nonpolar.